Okay, so what I want to talk about is invariant measures. That we will start with invariant measures of on a for a compact metric space. This is compact. If I consider a continuous function from t to d, thought of as a iteration. We thought of as a dynamics generator of the dynamics by on this compact metric space. Then I want to construct an invariant measure on X, mu from B to it could be zero and it could be infinity. The positive measure, which is regular, which is equal to constructing a function sort of is the integration, which is continuous in the supremum norm on Cx. So that is what we want to construct. So I start with any measure. Are we starting with any measure? Why do we have to start with any measure? Then what we have to do is sort of take the averages by push forwards of this measure by the iterations of t. So t is the transformation. But what it will do is, if I take this nth guy, the difference between, so I want to show it's a t invariant measure. I want to show it's approximately t invariant measure. What will happen is the average will be 1 by n sum of I 0 minus 1 and then this would be what would this be? Oh, they will cut each other off. So this sum is happening in this way. The sum is happening in the following way. If I take f equal to 0, uh, yeah. So this is I is equal to 0. So this will be this guy. Plus f composed with t square minus f composed with t. Yeah. So eventually, what will remain would be the first term and the last term, which means what will remain is this thing. Yeah, I think I can write this down now. Yeah, okay, let's do it. If you come back matrix space, I'm specifying CX dual because it means they're regular. I'm not really sure what kind of what regular means there, so I will do that later. But for now, we will just get a probability measure. Mm, yeah, fix any probability measure. Then this guy is extra compact, which means which will come later. Let's use it later. Consider mu n to be the average of j is equal to 0 to n minus 1 j. It's a push forward, so it's below. Yeah. Then mu n is in it's a probability measure. It's a average of a few probability measures. There is a problem with converging subsequence, but before that we need to prove some inequality, which is if I integrate on x this f composed with t minus f with the measure delta mu n, then what we'll get is 1 by n, the sum of minus 1, so t to the plus 1 I don't need any other brackets. I do need an integration. Now this means as we observed, this means if I have to just integrate this is what this means. No, this is the last term would be n plus 1 mod. Oh, okay. Forgot I defined a mod to remember. This means this is less than equal to twice addition on x mod. How is this coming out? Because if I take the mod, I will get twice of. So f composed with t to the power n plus 1. T is measure preserving, so t is out of 1. Yeah, if I take a measure preserving transformation, I can integrate and I will still get integral, which is precisely 2 by n of f infinity. Oh, okay, they're taking the measure. Huh, I think that is much easier thing to do directly. So, integrating supremum times the measure. Yeah, the modulus of this. Right. Now, if I just replace n with j, because dividing by nj, and nj is going to infinity, this is going to 0. Which means this is for all. If this number is less than equal to any number, any epsilon more than 0, then it's actually 0. So, we have to write something for that because I want to be super explicit here. Integration on x of f minus f. If I integrate with the limit, this is weak start limit. Some point-wise evaluation. So the integration is like the only thing that is the integration will limit. So mu n j is limit of nj tends to infinity would precisely be the integral. Okay. What does this mean? Okay, yeah. So this means this is 0. Tell me as the tell me pxt. Yep. Just take an average and it works. Um, yeah. So this is the game we play. Sort of, you fix a t and then we try to find a probability measure, or you fix a probability measure like the Lebesgue measure and try to look at all transformations which preserve this function. There are two games we played. This game is, I don't care what probability measure you give me. It just needs to be the a regular one, which means it's an element of cx2l. I don't know. Is that the, so I should be looking at the race representation theorem. Hmm. This is not the one we want to look at. I think we can look at these articles. Anyway. Mm, yeah. Locally competent house of spaces. This is a race representation theorem which says unique positive. So positive measures are coming from unique positive radon measure. Radon measure is a special function of CC. Locally competent house of spaces. Keep this here. Now hmm. For some cases, this is okay. I don't know how to use this Pointer recurrence to prove this. Counter example, but okay. Anyway, this compact measurable map and symbolic elements are extreme points. Nah, I'm not going to do that. Um, what we want to look at now is amenable groups. Mm. So group action is continuous. Group action on NX is continuous if this is continuous. Amenable groups are the groups. Look at the compact host of second countable group. Principal group. It is of every continuous group action on a compact matrix space X. As by continuous group action is fine. I don't need it to be by isometric or something. No, that is not what we want. Has G invariant probability motion. And now we want to prove that abelian groups are mean. So the previous proof was the amenability of the group Z. That's where because I would just have to increase the hypothesis by T being a continuous, T being a homeomorphism. And now we want to quickly repeat the proof. The proof is sort of exactly the same. What we want to do is consider averages again, but to pack it neatly into an argument, it's better to look at it this way. So for fix a G in the group and N, I want to look at the nth approximation, sort of, just this of this measure. So this will take a measure and give you another measure. So that means what we are doing is this is a continuous map, I would think. No, this is probably not continuous. This is just a map. Just some adding a few elements. Oh, this is a continuous. If I okay, so are these G J forward is a continuous map. Forward of measure should be a linear map. I don't know what they're saying, but anyway, this is the magic beasts are compact. Now I have to look at the big gap for n more than equal to 1. So, abelian group A, I will call it G. If I restrict yeah, so we want to can claim that the I write proposition because claim is literally should be written as propositions, but okay. Um, finite intersection property. We'll use this guy. How do we show this is a good question. Hmm, what do I index it with? Hmm. Because these guys commute, so that would mean that the image under here is no I. Hmm. Image. So the compose. So order doesn't matter here. Take any order. That the image under all these things is in the image of every AIs. That means hmm, the finite intersection is actually non-empty. Okay. Right. There is a family of compact sets, closed sets here. We just need closed sets with finite intersection property. Um, the intersection is non-empty. And uh, pick some pick something from the intersections, which means using the image image of something, then if I push it, subtract itself, subtract with it, that would be, why would that be? These things commute, that's why. Things commute. G dual. G dual. Push. Hmm. Both of them are probability measures. So mu minus g pushed. Mu has probability measure equal to n. This. Hmm. This is what we need to prove. It's approximate. This is a similar kind of. So in the proof I did for R measure, I used the same property to construct a measure. We are using again constructing a measure using this. Um, I did not use compactness there, but of something else. Locally compact outdoor spaces have R measure as for theorem I proved. Now, what do I need to do now? Yeah, so we proved it for huh, we proved abelian groups here. So this same So that the idea is the same proof of amenability of Z goes goes through for any abelian group like Zn, Sn, uh, sorry Tn, torus, anything, any Lie group action, any group action is by a abelian group has an invariant probability measure. It not might not be a smooth measure. It might that's a different question maybe. But these are all CX2L rough measures. I think that is not a terminology, but okay. Now what we want to show is compact groups amenable, which is easy because we know the Haar measure. Compact groups is a probability. Now consider the orbit map. Orbit is a subset which is G invariant. Not explaining what an orbit is. Not explaining anything. But okay. G maps to Gx. Then I will write mu for the Haar measure. Then this means if I push forward, what we want to show is let's say this is the group and this is the orbit. Hmm. So which means the measure is like only as support. This is what is the terminology. The support of the measure is in the orbit itself. I want no stroke. I want a blow. I want this. The transformation here is the transformation on the orbit is literally the left translation on the group, and the measure mu is the left group actions, by the way. I have to fix left group action. Huh. This is a probability measure, which means yeah, that's it. That this is all I want to talk about today. Um, yeah, probability functional. Hmm. Yep. G transmission here, the pre-image pretty much the same. And so this means I would always have a probability. Okay, what's this? This means I will always have an invariant measure. But this will not be a probability measure. It will be a probability measure if it's amenable. Yeah, that's about it. Yeah, I plan to make more talks like this. This one is done today. Oh, I can't take it. I will make it so that I can take it. Hide card. Where is the checkbox? Huh. It's done. Mm, maybe there will be a hyper. Some point of read it up, which has very low priority. Yeah, so I plan to uh, talk more about. So I think the next talk would be figuring out the orbits, and then I will talk about the obsidian template that I have that I made, and after that I will. This will be in the weekends. I'll probably do another thing on the weekend, and on Monday, next Monday, I will redo my stability geometry talk because yeah, and that's it.